Hello everyone. Today I and my colleagues are going to explain something about simulation and timing analysis. Simulation race. The word race could have different meanings in different contexts. In the context of HDL simulation, the word race means same HDL code exhibiting two or more possible behaviors, both of which are correct as per the language interpretation. So, a race implies ambiguity by its definition itself. Race says that there are multiple interpretations and all of them are correct. A simulator is free to choose any one of those multiple interpretations. However, it is not necessary that the final realization will match the interpretation that your simulator chose. First one is read-write race. Read-write race occurs when a signal is being read at the same time as being written into. First one is combinational read-write race and second one is sequential read-write race. Then another is write-write race. Write-write race occurs when the multiple values are being written into a signal at the same time. Then the next one is always initial race. Always initial race occurs when an initial block is updating a signal which also appears in the sensitivity list of an always block. Then next one is race due to interleaving of assign with procedural block. For this specific situation, different simulators are known to exhibit different behavior. When Q is updated to 0, the assign statement is supposed to re-evaluate the value of P. The way to resolve this ambiguity would be to put a delay before the dollar symbol displays. This delay specification will force the execution to move the assign statement before the executing the dollar displays. For avoiding the simulation race, we have to follow some steps. The first one step is when modeling the sequential logic, use non-blocking assignments. When modeling latches, use the non-blocking assignments. Third one is when modeling combinational logic with an always block, we have to use the blocking assignments. Then fourth one is when modeling both sequential and combinational logic within the same always block, use non-blocking assignments. Fifth one is do not mix blocking and non-blocking assignments in the same always block. Sixth one is do not make assignments to the same variable from more than one always block. Then seventh one is use the $stop to display the values that has been assigned using non-blocking assignments. Then last one is do not make assignments using #0 delays. Then next topic is simulation synthesis mismatch. What does it mean? Simulation synthesis mismatch refers to a situation wherein a given RTL showed some simulation results. However, when the same RTL was synthesized and the realized gate level netlist was simulated using the same vectors, it exhibited a different behavior. Some of the most common reasons for the simulation synthesis mismatch included: first one is races, as explained previously. The second one is explicit timing in RTL. It says that the RTL code had an explicit delay assignment. When synthesis is done, the functionality is realized using the technology gates. The delay for these technology gates could be totally different from what was specified in the input RTL. And if the functionality was dependent on the delay values, then it is possible that the same functionality might no longer be visible after synthesis as the delay values have now changed. Then third one is the missing sensitivity list. The RTL code segment below is for the combinational block that misses some signals in the sensitivity list. Then next one is the delta unbalancing. It is possible that the RTL was written using the balancing of deltas. However, during synthesis, the tool did its own adjustments in the terms of inserting some additional buffers to meet the load requirements or removing certain gates to improve the timings. These adjustments could modify the delta balancing. Usually, this is not encountered too often because most designers use Verilog for the gate level and this issue of delta balancing does not come into the picture. Then next one is the initial block. What does it mean? Synthesis simply ignores the initial block. So if an initial block is used to achieve a desired functionality at RTL stage, then the realized gate level netlist will not exhibit the same functionality. Usually, initially block should be a part of test bench used to initialize the circuit through the external inputs rather than being a part of design itself. This same test bench will then be able to initialize the gate level circuits also. Then next one is dependency on the X. X or X is something that is visible, that is always available only in modeling. In the actual hardware, there is no such things as X. So, if a don't care value is being assigned or checked for in RTL, the same behavior might not be visible in the synthesized gate level netlist. Then next one is comparison with the unknown. A comparison with X or Z could result in the simulation synthesis mismatch. X does not have any counterpart in the physical world. Z means tri-state, but usually in the physical world there will be some value available on the net. So comparison with tri-state would not have any meaning in the physical world. Then last one is careless use of variables. In the VHDL RDL code, variables are not allowed by the language to cross process boundaries.
Now I am going to explain about timing analysis. Timing analysis of an ASIC design is accomplished through simulation. Timing analysis involves applying a set of vectors and checking whether different signals are present at the desired time at various points in the design. Disadvantage of this is it depends on the designer's knowledge of test vectors. Now STA. So around mid-90s, static timing analysis emerged as a better alternative to tackle increasing chip complexities. STA computes the range of timings within which the signal will be available at various points in the design and compares them against the required time. Now, scope of STA. The scope of STA is that it is present only to validate the ability to meet the desired timing goals. STA does not deal with any logical functionalities of the design. Next is simulation limitations in the context of timing. Design's functionality is validated using RTL simulation, but RTL does not give detailed timing information. It only understands cycle accurate, which means it knows which signal reaches where in how many clock cycles. Again, it is only applicable for portions which are synchronous. Also, cycle behavior is assumed and not validated by simulator. Even gate level simulation are not very reliable for predicting the design's ability to meet the timing. The fundamental issue with simulation is ensuring exhaustiveness of all the applied vectors. Now the next is exhaustiveness of STA. STA computes both the minimum as well as the maximum range of delays values for all possible combinations of input. Hence, it does not depend upon a designer's knowledge about vectors and could only fail due to incorrect specifications. Moving on to timing parameters for digital logic. On real CMOS devices, the circuit actually exhibit analog behavior. Digital behavior is an abstraction or modeling technique which makes the analysis simpler. Some of the parameters are delay parameters. Delay is defined as the time between the application of an input and the observation of the response at the output. When a transition is applied at the input, the output would show the corresponding response after the corresponding delay. Inertial delay is glitch at the input is not reflected at the output. Next is transport delay, where the glitches at the input are transmitted as it is at the output. The other parameter is slew parameters for digital logic. Slew refers to the time taken for the signal to go from 0 to 1 and vice versa. The slew specifications should include the points at which measurement was started and at which the measurement was stopped. The next parameter is delay and slew measurement. Delays and slew values are available in the library, so STA engines can obtain these values from the libraries. Delay and the slew value is measured against a lot of parameters which affect their, and the corresponding values are stored in the library.
Now I am going to explain factors affecting delay and slew. Delay and slew through gate are impacted by many discrete and continuous factors. Some of the important factors are discrete factors. In discrete factors, we have gate geometry and schematic. The geometry of a gate refers to a physical dimension of the transistor used to form the gate. Geometry is usually a function of the specific technology. For example, 90 nanometer is a different geometry than the 45 nanometer. Geometry has a very significant role in deciding the roll through the gate. Lower geometry means faster the gate. Schematic refers to the interconnection of the transistor within the gate. So, a NAND gate will have lesser delay compared to the AND gate because AND gate has an extra stage compared to the NAND gate. After that, specific path. Different paths of a gate have different delays. For deciding the delay of a gate through a gate, you need to know the path which is interest of you. Sometimes for a gate where the inputs are interchangeable, depending upon the performance desired on a specific path, a choice might be made as to which input pin should be connected to it. Next one is specific direction of the transistor. For a combination path, the following combination may be possible. For input rising, there must be output rising. For input rising, there must be output falling. For input falling, there must be output rising. And the last one is for input falling, there must be output falling. Note, all these paths are always possible. The last one is conditions on other pins. Sometimes the delay through a specific arc is also dependent on the conditions of some other pins. In such a case, a specific arc might have different specification each for the condition of other pins. Example of such arc could include a synchronous clear to flop output when clock is equal to 0, a synchronous clear to flop output when clock is equal to 1. Next, we will discuss about the continuous factors. In continuous factors, we have load on the gate. The delay of a gate depends on the load that the gate's output is seeing. The load seen by the output is sum of load of all inputs that this input has to drive, load of the interconnect wires which connect the output to all other portions of the circuit. If this is transistor output, then there might be other tri-state cells output also connected to this output. Those outputs also put the load. Usually with an increasing load, the delay also increases. The next one is input slew. The delay of a gate depends on the transition time at the input of the gate. The transition time seen at the input of a gate is dependent on the following factors. Transition time at the previous state, that is driving this input. The interconnect which determines how the slew gets modified as the signal transfers over the interconnect wire from the driver gate till the output pin. For a primary input, the input slew is specified. Such factor might include. The next one is temperature. Usually, delay increases vary marginally with an increase in junction temperature. Junction temperature refers to the temperature within the silicon. In general, the junction temperature is higher than ambient temperature, which refers to the temperature of the environment in which the chip is being used. The next one is voltage. Usually, delay increases significantly with the decrease in supply voltage. In this context, supply voltage refers to the voltage at the gate. There might be a slight drop in the voltage by the time it reaches the gate compared to what was applied at the supply of the chip
due to drop through the power rails. Next one is fabrication process. The manufacturing process involves some statistical variation. Some portion of the die might receive very strong doping, while some other part portion might receive a weaker doping. This statistical variation called as the process variation. Next one we will see sequential arcs. Delay relate to the input reaching an output. However, sometimes there are timing relationship between two input themselves or multiple edges on the same input. This relationship usually exists only for sequential cells. These are various kinds of requirement that need to be satisfied so that the sequential cell behaves reliably. In sequential arc, we will see pulse width. This refers to the minimum width of the clock and synchronous pin so that the sequential cell can register the clock or an assertion of the asynchronous pin. For a clock pin, this check might refer to the both low pulse as well as high pulse. For a synchronous pin, low synchronous pin reset, there would be requirement of minimum width for low pulse. If a pulse is applied which is of duration shorter than the minimum pulse width, the output may not go to the desired level. That is, clock might not be able to capture the new data, or the asynchronous signal might not be asserted. The next one is setup. This refers to the minimum duration before the triggering edge of the clock by which the data should have come stabilized. Alternately, this refers to the time before the clock edge and the till clock edge during which the data should not change. If the data changes within this duration, there is no guarantee that the new data would get captured in the sequential device. The next one is hold. This refers to the minimum duration after the triggering edge of the clock till which the data should retain in its stable value. Alternately, this refers to the time after the clock edge starting from the clock edge during which the data should not change. If the data changes within this duration, there is no guarantee that the new data would not interfere within the data being captured within the sequential device. Next one, recovery. This refers to the minimum duration after the deassertion of a synchronous control signal, during which the clock's triggering edge should not come. A good way to understand this is, suppose the synchronous control signal has been deasserted. However, the circuit is still not recovered from the effect of a synchronous control signal. So, if a clock triggering edge comes before the circuit only full recover, the clock edge may not really trigger the circuit.